So the third paper is data-free knowledge distillation for using recommendation model. This paper addresses a relevant problem of model retraining and privacy concerns of all the training data. The presenter is Cheng Wang from Huazhong University of Science and Technology.
Okay. Hello, everyone, and thank you for coming. My name is Chen Wang. First of all, thanks for the session chair and everyone who provided us a great RecSys ceremony. So today's topic is about data-free knowledge distillation for reusing recommendation models. So here are the collaborators from Huazhong University of Science and Technology and Huawei NOAA ARCS Lab. So I really appreciate the help from Dr. Dong Zhenhua and Dr. Sun Jiachen during their internship in Huawei, and thanks their detailed guidance from Professor Rui Xuanli. So I will introduce this work from 4 parts. First is the background. Okay. So, as we all know, users frequently interact with popular online services. So the preference of user may change from time to time. So to provide personalized recommendation, the service provider needs to periodically refresh the model. So the existing work about handling the dynamic nature of user preference have the following method. So first is the fine-tuning. So it updates the model based on the new interactions only. So as shown in the right, so the fine-tuning refreshes the model with newly collected data in each period. And since it's only use latest data, it can easily cause the overfitting and forgetting issues. Another existing work is about sample-based retraining. So it selects representative data and adds them to the newly interaction to retrain the model. So sample-based retraining, it always depends on some strategy and may lead to the suboptimal, right? Then is the most straightforward method. That is the full retraining. It updates the model with all historical data and the new collected interactions. So as we can see, all the existing methods are trying to find a non-trivial trade-off between the usage of data volume and real-time deployment. So what if we have an expert that can provide us a small batch of informative data from history and added them to new interactions to form the whole training data? So fortunately, we have the historical model, which have been encoded with plenty of historical data into their parameters, right? And as we can see, the historical model have used many computational resources and used many time to training this model, but it seems few people notice that this model are very treasure for us. So today I want to tell you how to reuse the model and to tell you a story about data is model, model is data. So then I will introduce some preliminaries about model inversion. So maybe someone knows model inversion is a novel way to recover informative training data with similar distribution as the raw training data. So in recent years, some researchers in computer vision start to adopt model inversion to recover training data. So let's take a simple linear regression as the example. Here we have some blue data points, and the red line is the model parameter. Yeah, different from the model training that updates the parameter theta. In the process of model inversion, we freeze the parameter of pre-trained theta and update the input. We only need to start from a random initialized point x0, and we put the x0 into the pre-trained model and update it with stochastic gradient descent, so to lower the loss, and the x0 will gradually converge onto the red line. So why do we need to use the model inversion? It has the following advantages. So first is, with only the pre-trained model parameters, we can generate informative synthetic data. Another advantage is it is a data-free way to avoid the historical data management and a good way to reuse recommendation model. So here, I will detailedly introduce the overall framework of how to adopt model inversion to reuse our recommendation models. Oh, sorry. So here, I will introduce some preliminaries. So first is the click-through rate. Click-through rate prediction is to predict the probability that a user will click on an item under specific context. So the click-through rate always, many researchers consider click-through rate as a binary classification problems. CTR model usually will use the embedding table and some neural network paradigms. So as depicted in the equation 3, the goal of CTR prediction is to learn the parameters of the function f theta to minimize the objective function. So every embedding-based CTR model will have an embedding table. The embedding table, we will use the embedding table to transform the one-hot encoded vector of categorical features into the low-dimensional dense embedding. Okay, so the question is, oh, let's have some mistakes, sorry about that. So how can we use the model inversion to implement it on our recommendation model? In the CTR prediction task, the goal of model inversion is to optimize the user UI's one-hot vector and item VJ's one-hot vector as shown in the figure equation 5. However, the discrete one or multi-hot recommendation data would block the gradient flow, causing the backpropagation chaining to be invalid. So the figure on the bottom has shown this problem. So suppose we have a pair of data UI and VJ which have been encoded into one-hot representation. When the data instance passes through the CTR network and backpropagate with stochastic gradient descent, the gradient flow will be blocked in the last layer. So how can we solve the gradient flow block problem? So here we design a new data format and we consider two attributes it should have. So first, it should be in a differentiable manner to be successfully optimized during inversion. And the second, we consider the generality of the proposed framework. So the new data format is showing in the equation 5. It is a simplest way that we convert the original one-hot data representation into a dense and continuous data format. So the equation 7 is our final optimization formula. So our aim is to reuse the historical model. So the information that we distilled from the historical model, we want it to have the informative information to help us for the downstream task. So the first important question is, how can we make our data more informative and diversity? Because diversity plays a crucial role in avoiding repeated and redundant synthetic data. So we use a very easy trick, and we add an additional gradient freezing trick. So it can also be recognized as a conditional model inversion. So while we optimize the mu, we freeze the mu and the user's random user's feedback, and we use this formula to optimize our synthetic data. So another important question is, how can we prove that our data has the good quality and help us to the downstream test? So in this problem, we use mostly use the batch norm layer and use the statistics in the batch norm layer, like the mean and variance. So we want our synthetic data to match the original data, the distribution of the original data. Yeah. So The overall framework of our proposed method is we first initialize the random input with the new data format and then implemented the gradient freezing trick and the statistic of the Brecht norm to optimize the informatively synthetic data with only the historical model. Yeah. So then I will introduce some experiments results. So to answer the question about is that really a good way to reuse the historical model? So to answer this question, we from three perspectives. Perspective one is the regression one. So how is the quality of the synthetic data generated from our framework? Question two, how effective of our framework is in distilling informative training information from the pre-trained model? Question three, how is the performance of the inverse synthetic data compared with other sample-based model retraining methods? So since reusing the historical model is a new task, so we select different baselines to compare our method to other baselines. So to answer the research question one, we use some generative method to compare with them. So first, our framework can be realized as a generative model that can synthetic informative data from pre-trained model. So we compared with the following baseline, and we can find an interesting. We have an interesting finding is that. So with only 2,000 hours synthetic data, our performance is outperformed than the other baselines. So we have achieved our first goals. We used the historical model and we distilled some very important informative data from the historical model. Yeah, that's the first. And second, we also, since our method is a data-free way, right? So we compared the most recent data about data-free model extraction. And we also find that with 2,000 hours synthetic data, it outperforms the existing baselines. So, and we find another application about model retraining. So why do we need to reuse the historical model? We want to use the historical model to finish some downstream task. So this experiment is about how our distilled informative synthetic data can help the downstream task. And we find an interesting result is with only a few of synthetic data, we can have a good performance in the downstream test. And then we have some ablation study to tell you why the gradient freezing trick is work, and use the T-SNE visualization to tell you the importance of the gradient freezing trick. And we do some experiments about the data, different data scales. So what can we find in this paper? In this paper, we first investigate an interesting but seldomly discussed problem. That is to say, how to reuse and transfer the variable information that is included in historical model for various downstream applications. And we are the first to attempt data-free knowledge distillation to distill informative synthetic data through a pre-trained model on the recommendation field. And the new data format may open up a new window for recommended sister fields. And the perspective of the reusing the historical model maybe open up a new track to all the researchers to focus on it. Last, we thank the anonymous reviewers for their expert and constructive comments and suggestions. And we thank the support of National Natural Science Foundation of China with the foreign members and the Science and Technology Support Program of Hubei Province under the members. And if you have any question, please feel free to contact me. Okay, that's all.
Thanks so much for your very nice presentation. Okay, please,
Yeah.
Joe.
Yes, Joe Constant, University of Minnesota. I love the clever technique that you've used, and I understand the evaluations that you did, but I want to understand the big picture. If you were the ones who trained those models, those historical models in the first place, you would have the data that went into those models. Did you do any comparison to look at both the quality of performance and the computation time performance, advantages or disadvantages of reverse engineering, basically, your model to come back to synthetic data versus just keeping the old data and using it directly?
Yeah, maybe I already understand your question. So in the experiment, we have compared our method with some sampling-based method. Yeah, what is sampling-based method? It selects some historical data and using it to the downstream task. And why we need to reuse the recommendation model? So first, as all we know, recommendation data is too many. Yeah, we can get too many recommendation data daily. So we have many of data. So the question is to management the data and to storage the data is a big problem, right? So if we have a condensed historical model and it encoded many historical data into the parameters, maybe we can use the historical model to do this thing. And in the experimental result and shows our method is outperformed than the already existing sample-based baseline. Yeah.
And did you also look at the time performance of it?
Yeah, we have do the time we have compared the time, but we didn't show it in the our current paper, right? The experiment result is with our things. Since we only need a small batch of synthetic data, our performance can better than the existing baseline, and we can use less time. Yeah.
Great, thank you.
Yeah, thank you.
Any other question? I have just a curiosity about your models. Since it seems that it is not specifically tailored for the recommendation task, it could be also exploited for other machine learning tasks. What are, in your opinion, the peculiarities for the recommendation scenario? The particular characteristics of your model for the recommendation scenario?
Sorry, I didn't understand your question. So what are you aiming for? And
I guess that this model could be also exploited for other domains or tasks.
Oh, you mean the cross-domain task?
Mm-hmm.
Okay. Oh, okay. In our paper, we only do the research about only one domain. Mm-hmm. So the cross-domain problem, and we have already under our calendar, and we are doing this, and we find use the model inversion in the cross-domain recommendation. It has really a good performance, and it can protect the user's privacy. Yeah, that's a very interesting. Yeah.
Okay, thanks. So no question from the online audience. Okay, thank you very much.
Okay, thank
you. We can move to the last paper, last and fourth paper, that is online matching a real-time bandit system for large-scale recommendations.